Okay, my friends, we'll go ahead and begin. Sorry, I had to unmute myself. Okay, good. So we have been, whoa, that's a little loud. We have been talking about the Homo of the nucleophile attacking the Lumo of the electrophile. Recall that we've developed some shorthand for looking at a molecule and determining what the reactive portions of that molecule are. We're looking for high energy filled orbitals and low energy empty orbitals. And so we start by looking at, and any given molecule might have some of these and not others, right? Not every molecule has a pi bond, so not every molecule has a pi orbital or a pi star. In any case, we start looking for the highest energy electrons by looking for lone pairs. If it doesn't have lone pairs, we start looking for pi bonds. If it doesn't have lone pairs or a pi bond, chances are it's not a particularly good nucleophile. In terms of electrophiles, we start looking for empty p orbitals like we saw for boron-containing compounds. We haven't seen carbocations yet, but we will. If there's no empty p orbital, we start looking for pi stars or for carbon halogen sigma stars, which can be low in energy. And if it doesn't have an empty p orbital, a pi star, or a carbon halogen sigma star, chances are it's not a particularly good electrophile. So I showed you some examples last time of reactions that you can actually predict now based on this simple understanding of orbitals. One of them was if we take, say, hydroxide and then this alkyl halide, you've got a methyl group with a chloride attached to it. And based on the analysis above, if I told you that the OH minus was the nucleophile and that the alkyl halide was the electrophile, you would have gone and identified that the HOMO of the nucleophile is likely lone pair electrons on the oxygen. The LUMO of the electrophile is the carbon-chlorine sigma star. That's the lowest energy empty antibonding orbital that we have. And then, based on the the second great commandment of OCHEM, HOMO attacks LUMO, you have electrons from the HOMO attacking the sigma star, making a new bond between oxygen and carbon. Because it's a sigma star antibonding orbital, when we use it to make a new bond, we have to break the corresponding sigma bond, the carbon-chlorine sigma bond. Some of you asked at this stage, why does the negatively charged oxygen attack at carbon instead of chlorine? The answer to that was first that if you pay attention to the electronegativity difference between carbon and chlorine, you've got a delta positive, a small partial positive charge on carbon because chlorine's more electronegative than carbon. So it makes sense just in terms of repulsion and attraction of like charges that the nucleophile would attack the carbon where the delta plus is. Yeah?
Will we have to figure out which one's the nucleophile and which is the electrophile?
Will you have to figure out which one is the nucleophile and which one's the electrophile? Yes, though it's okay if right now that's a little bit unclear. You'll get it by experience. Okay, what else? Others? The second reason why the nucleophile hydroxide doesn't attack chlorine is because the products that would occur if that happened aren't as stable as the ones we get if we attack carbon. And again, that might be a little unclear. We'll talk about that and get to that later. So this was one example, and if you know what a sigma star antibonding orbital is, then you could have predicted this product, this alcohol, with Cl minus having left. And this is a substitution reaction. We did a few others. There was the simple sort of BH3, which is trigonal planar, and as I think we said last time, the LUMO has to be an empty unhybridized p orbital. the reason that has to be the case is you can look at boron. It normally has 3 valence electrons. It currently owns 3. Formal charge is 0, so actually there's no lone pair on boron. You've used each of the sp2 orbitals on boron to make these boron-hydrogen bonds. What's left over is this empty p orbital that doesn't have any electrons in it, but nevertheless is there. And then I can't remember which particular nucleophile we used, but if we used water as a nucleophile, the HOMO would be the non-bonding lone pair electrons on the oxygen. HOMO attacks LUMO. When you have the HOMO of a nucleophile attack an empty atomic orbital, you just make a new bond. There's no need to break another bond because this isn't an antibonding orbital. It's simply an empty p orbital. So in red is the new bond that we made. And all we have to do is make a few adjustments in formal charge. The oxygen should now be have a positive formal charge on it, and the boron should have a negative formal charge on it. Yeah?
Just to make sure, we're talking about 52Ps. Is that only going to be relevant for, assuming we're just talking about 2P row, just boron and cations and anything else?
Well, let's see. When are you going to find an empty p orbital? Boron and then positively charged trigonal planar carbons. We won't see that a lot with nitrogen and oxygen and fluorine. As you go down the periodic table, would we see something similar? Silicon and aluminum can behave very similar to boron and carbon, respectively. Yeah. Okay. Others? So I think one of the ones that I left you with to ponder on, and we were starting out with some sort of aversion therapy stress inoculation with the 6-membered ring that has a double bond in it. And I think I told you that you have a nucleophile here and an electrophile here. So, based on what we've talked about, what is the highest occupied molecular orbital of the nucleophile? Pi, right? It's the pi, carbon-carbon pi bond. Good. The lowest unoccupied molecular orbital for HCl is what? Okay, some of you said lone pair. That's a filled orbital, and there are lone pairs on the chlorine, but that's not an empty orbital. The only empty orbital you've got in a molecule with one bond is the corresponding antibonding orbital, right? It should be the carbon, chlorine, sigma. That's not carbon, it's hydrogen, chlorine, sigma star. Okay. It may be useful to draw what that sigma star looks like. Give myself a little space. There would be a node in between the hydrogen and the chlorine. There would be a small lobe here, a large lobe there, and then there would be another lobe here. This is what a sigma star looks like when it involves hydrogen. Now we can look at that and say, well, the sigma star is both on hydrogen and chlorine, but we can make a prediction about where the sigma star is most reactive, and we would say it's on the hydrogen because of the electronegativity of chlorine. What would the pi bond look like? What would the pi orbital look like from this viewpoint for our alkene? We would have sort of a continuous lobe of electron density above the plane of the double bond, and then below we would have another orbital lobe with the opposite wave function sign. If we looked at this sort of side on, we could also draw it just like two p orbitals side by side. either of those drawings communicate things. Okay, so what should my arrow do? What do you predict will happen in this reaction if we keep the OChem commandments? And I'm sorry, I just went to the Hamilton. OChem commandments. Okay, sorry. Go ahead.
So the pi bond will attack the hydrogen.
Okay.
The thing, yeah, and it will cause that bond to break.
And should cause this bond to break. Good. So that's exactly what happens, and we're not even going to get to that reaction till chapter 10, which is surprisingly soon, given the fact that this is a spring semester. When you draw a mechanism like this, the arrows tell you what happens to the bonds, and so if you know the arrows, you can predict what the next step is. For example, I've showed the bond between hydrogen and chlorine breaking. So what should happen to chlorine? Just takes those electrons with it. It's there on its own. So one of our products is Cl minus. Okay, now the other one's a bit tricky because we made a new bond between these electrons and hydrogen, but those electrons were initially shared between the two carbons. So what do you think the product looks like? Go ahead.
Bond breaks, so it would just have hydrogen hanging on and be a positive charge.
So you're saying that since you've got atoms A, we'll say, and B of our alkene, they used to be shared, we're making a bond. One of those atoms gets the hydrogen and the other doesn't. Now, already, the what-ifers among you were saying, well, what if the two carbons are not the same? And I'm saying, don't worry about that. We'll handle that situation in the future. There's a pretty simple rule for that. But let's just say that we've got one of those atoms has to get the hydrogen and the other, because it no longer has the electrons that were involved in that pi bond, should have a positive charge. And maybe, I don't know if it'll be helpful to draw in the hydrogens that were implied but not shown. Let's just go ahead and put the new hydrogen on atom A, and then atom B is still surrounded by three things, only owns 3 electrons, but usually comes with 4, and so should have a positive formal charge. Okay, does that make sense? For those of you who want to know about more complicated things, actually sometimes there's an intermediate. For some of these types of things, there's an intermediate where the hydrogen just sort of sits down there in the middle of the pi bond and is shared between the two atoms. You've got 3 atoms sharing 2 electrons. It's a 3-atom, 2-electron bond. And if you want to know more, sign up for my Chemistry 552 class in the fall. There's going to be a lot of takers for that, I can tell. Okay. Good. Questions about that? Yeah.
How would this work with the energy orbital diagram?
How would this work with the energy orbital diagram? Let's see. Well, before, for the nucleophile, we had a pi bond, right? And if we think about that, that pi bond came from overlap of a p orbital on carbon A with a p orbital on carbon B to give you this pi bond, and we'll say it's got electrons in it. The empty orbital is the sigma star, and that came from overlap of an orbital on chlorine, probably one of the p orbitals on chlorine with 1s orbital on hydrogen. Okay, and electrons are, when we formed that bond, electrons moved down in energy. So here's sort of the situation we have. And what basically happens is, as this reaction proceeds, we're going to slide these electrons in the pi bond back here. We're going to slide these electrons here. and then we're going to make a new bond between the p orbital on carbon. I got mixed up, right? Because we said it's with A, so whatever. We make a new bond with the p orbital from A and the 1s orbital from hydrogen. And here is our new carbon-hydrogen sigma bond. And then chlorine leaves with its electrons. It's got a negative charge. And then over here we have just the empty p orbital from carbon B. I don't know if that...
Because wasn't there a way to... Didn't we have to break the pi bond?
Yes.
And wouldn't that be the electrons going into the pi star?
Do you have to break the pi bond? Does that mean the electrons going to the pi star? No. What happens is the pi bond attacks the hydrogen, and we take those electrons that used to be in the pi bond, and we now use them for a sigma bond.
Okay, so that's what's happening.
Yeah. If all of this stuff down here didn't make sense, that's okay. It didn't make a whole lot of sense to me either. So, okay, other questions? All right. Now, I told you that once you did this first step, you would get some intermediates, which themselves are nucleophiles and electrophiles. So, nested problems of OChem are always fun. Keep peeling away layers, and there's even more inside. So, let's see. Sorry, I just got distracted by something my son told me. He was his first year at BYU. He just finished up, and he told me that he feels like the MARB is bigger on the inside than it's suggested by the outside. So it's like OChem too, right? That's neither here nor there. I'm really sorry. So if you looked at these intermediates, which do you think is the nucleophile, and which do you think would be an electrophile? Yeah. Chlorine, because it has lone pair electrons that are high in energy. That's exactly right. Also, it has a negative charge. Sometimes you can identify nucleophiles because they have a negative charge. All right, then the other one would be the electrophile, and you can tell because it has a positive charge. The other reason you can tell is if you look at this carbon, the carbon is surrounded by three things. It's got a positive charge. It's trigonal planar. You're using each of the sp2 orbitals in the sigma bonds. So what you've got left on that carbon is an empty p orbital. And that p orbital would look like this. If we're taking the view from above, we'd have a lobe above the plane of the page, and another lobe below. Oops, we're going to need to decrease our font size there. Another lobe below the plane of the page. And if we were looking at this from the side, what would we see? I guess this is A and this is B. Would look like this. The colors here just represent a change in the sign of the wave function, and they help us realize that there is a node in the plane of the carbon and carbon-hydrogen bonds. Okay, so now make a prediction. Go ahead.
Yeah, so I just have a question. How do we know it's an empty p orbital and not just that it has lone pairs?
Okay, the reasoning there involves hybridization and formal charge. And it's actually formal charge first. So the fact that that carbon is positively charged, what does that mean? Well, to do that, to figure that out, you have to remember how formal charge is calculated. It's the number of electrons that an atom normally has, number of valence electrons, minus the number of electrons it currently owns. And an atom owns all of its lone pairs and half of its electrons, half of the electrons in its bonds. Okay? So carbon normally has 4 valence electrons. The formal charge is +1, which tells us that then carbon only owns 3 electrons. And I can account for each of those 3 electrons in each of these 3 bonds, 1, 2, and 3.
It's not kind of weird with like the octet rule.
Yeah, oh yeah, this totally breaks the octet rule. It has fewer than 8 electrons.
Okay.
Yeah, you can't go bigger than the octet rule. If you have fewer than 8 electrons, chances are the molecule's reactive. Right? We would call this a hypovalent carbon, meaning it doesn't have a full octet. And we saw that before, by the way, with boron. Same thing here. The only difference is boron is neutral when it only has 3 bonds, whereas carbon, if it only has 3 bonds and no lone pairs, is positively charged.
So because it has like a positive charge, we realize that it's like something's off.
Right.
That's kind of the case we're saying with the Trigonal planar.
That's exactly right. So because the positive charge is on that carbon, that's how we know that something different's going on here. So just to review, you calculate formal charge with number of valence electrons an atom normally has versus minus the number it owns. We know there's a positive formal charge on carbon, so the answer is +1. We know carbon normally comes with 4 valence electrons, which means it must only own 3. And I've got 3 bonds, and so all 3 of the electrons that we own come from those bonds. Therefore, there's no lone pair on the carbon. Based on that, then you say, okay, only 3 groups, so has to be trigonal planar, meaning there's 3 sp2 orbitals and 1 unhybridized p orbital, and I account for each of the sp2 orbitals in each of these sigma bonds, so what's left over is the 2p orbital that can't have any electrons in it because there's no electrons there. Yeah?
So does that mean like the reaction to get this molecule is like really unlikely?
Does that mean it's good?
It's like more likely to like go back?
Great question. Does that mean this reaction is unlikely or like maybe prefers to go backwards? In fact, I mean, the answer is yes. Getting to this point, getting to the carbocation, if you were to draw an energy diagram where you said, okay, on this x-axis, I'm going to have some number that represents progress of the reaction. Yes, here's your starting materials, and that would, going to the carbocation would require you to go uphill. Now, the question as to whether you'd go back downhill or whether you can go back to eat something else too, we'll see. Yep. We'll generally see in this class carbocations are high energy intermediates, not particularly stable. But okay enough for some reactions. Right, other questions? So let's go ahead and predict the next step. Nucleophile, electrophile. You tell me where the arrows go. From chlorine to
the positive charge.
Come on, I need some direction. Okay. To the positive charge. Okay, so when you have a pair of electrons attacking an empty orbital, you just make a new bond. There's no need to break an old bond. Do you have to go? Yeah, you have to follow that. That is the exact path which you must reproduce. No, come on. Oops, that was the eraser, not the pen. Okay, that's fine. And here's an interesting issue, which again, we're not going to get to till chapter 10. What do you notice about that carbocation, that p orbital? Which side do you think chlorine attacks from? Because you got 2 possibilities. Positive side? No. Well, actually, remember, wave function sign doesn't have a physical meaning. It just means that the sign switches and you've got a node in between. So we can attack, go ahead. I'd rather you say it than me say it.
I was just thinking if you have a hydrogen there, then it's going to go to the other side because it doesn't want to complete it anytime soon. So I don't know if that hydrogen is going up.
Okay, are you thinking about the influence of these hydrogens here?
More so the one on the left.
Okay.
I can't tell if that one's going down.
Okay. No, good. That's an error or a problem in my drawing. It's trigonal planar, so the hydrogen and all the carbons are flat. So go ahead.
Couldn't it attack either orbital and then the hydrogen moves accordingly?
Yep. So the lone pairs on the chlorine could attack from above or below. And then, depending on which way you go, you're going to have, maybe we'll take the top view because that'll be easier. You'll either have the chlorine up or the chlorine down. Now we're going to learn how to deal with this situation. Those are actually exactly the same molecule in this case because you can flip one over and it becomes the same thing. We're going to talk about that in chapter 5. There are going to be some molecules for which those two possibilities will not be identical, and we'll have to deal with that. But see, already, if you understand Homo and Lumo, you're already able to make some pretty sophisticated predictions about what the products ought to be. And the fact that you know now that you can attack that p orbital from above or below, that's a fairly advanced concept in 351 that you already sort of have based on these initial principles. Okay, maybe one last preview of reactions. I'm going to show you an aldehyde, and this is fine. We're going to continue to use, I can't decide what to do. Let's use this alkoxide nucleophile. I'm abbreviating this, but this is just a methyl group attached to oxygen. It's the conjugate base of an alcohol, okay? And I will go ahead and tell you that the negatively charged thing is the nucleophile and that the carbonyl compound here, the one that has a carbon-oxygen double bond, is an electrophile. Okay, so the easy one, what is the highest occupied molecular orbital of our nucleophile? That's easy, lone pairs on the oxygen. How about the LUMO of the electrophile? Pi star. Go back to our graph, whoops, or picture. If you're looking for empty orbitals, you start by looking for an empty 2p orbital. We don't have boron and we don't have a positively charged carbon, so we got nothing there. We start looking among the antibonding orbitals. We don't have a carbon halide sigma star. We do have a carbon-oxygen pi bond. And for reasons we will discuss later, carbon-oxygen pi stars are lower in energy than carbon-carbon pi stars. Won't matter right now for this discussion, but the electrophile is the carbon-oxygen pi star. If we were to draw that, what would that look like? Well, it would have a node in between the two nuclei, and it would have lobes on oxygen and on carbon, both above and below the plane of the page, and we would show opposite wave function signs to indicate where those nodes are. And if you were to look at this from the side, what would you see? What would the pi star look like? Again, we would have a node in the middle. That is a really terrible 3. Oops. That's not the same color orange. That's irritating. Okay. All right. So we would show Homo attacking Lumo. Now, we've got a similar issue as we had with sigma stars previously. The Lumo is shared between two atoms, so we have to decide where the nucleophile attacks. Should it attack on the carbon or the oxygen? And you can use electronegativity to help you think through that. Oxygen's more electronegative than carbon. So you would predict there would be a partial positive charge on carbon, partial negative on oxygen. The other thing you can do is draw a resonance structure in which you move the pi electrons out onto the oxygen and you get this alternative resonance structure. It's certainly not a great resonance structure. It's a minor contributor, but it does sort of represent the reactivity of this molecule. You expect it to be electrophilic on the carbon. So with that in mind, if my nucleophile attacks the carbon, attacks the pi star, what should happen to the pi bond? Got a break, electrons go out onto the oxygen. What is my new product? Well, the new product has a sigma bond between what used to be my nucleophile and the carbonyl carbon, and then the oxygen should now have a negative charge on it. And you're not going to get to that till 352, but it's the same basic principle. Homo attacks Lumo. All right. Anything more we want to say about that? Yeah.
What are the orbital codes you drew on the top of that? That was just a quick.
So this is, I've drawn the carbon-oxygen pi star. This is a view from above.
Okay.
This is a view from the side.
Okay.
Alternatively, you could just draw a pi star as though it were two p orbitals, and you just switch the wave function signs to indicate that there's a node in the middle. All of those are okay.
What was that to help us with drawing that?
Why would we draw that? Well, you're going to get so you don't need to.
Okay.
But drawing the pi star helps me remember that it's an anti-bonding orbital, and therefore when I attack it, I have to break the pi bond. You saying, why are we drawing orbitals? You don't even need to. Okay. You don't understand how drawing it gets you there. Okay.
But I get why it needs to be broken.
Okay.
Yeah, how important is drawing them? Because that's like my question as well.
How important is drawing them?
These are the examples.
Well, so good question. My exams tend to be multiple choice because that allows you to get instant feedback. It also allows me to give partial credit uniformly to the class. And it also ensures grading consistency. You do lose a little bit because you don't actually have to draw anything if you don't want to, though the questions are written such that if you don't know the material and you can't draw stuff on your own, it's probably going to be hard. I've definitely asked multiple choice questions where which of the following options is the Lumo of this molecule, and I show you a bunch of orbitals and you have to pick. So drawing them / recognizing them is an important skill. So to answer your question, why is it important to draw the orbitals? In this case, it may not look like it is, though drawing the orbital in this problem helped us see that the chlorine could attack from above or below. And that's an important conclusion. There will be similar issues with attacking carbonyls. Drawing the pi star would help us realize that that nucleophile could attack from above or below. And that doesn't have really any consequences for this intermediate that we need to worry about, but it can. And so that's another thing that drawing the orbital can get you. Go ahead.
So, how do we know which of the two possibilities there to draw in? Because I definitely drew the second one, and then saw in the answer key that the first one was the one that they put.
You drew which one?
The lower option, that it attacks the carbon.
Attacks from below?
Yeah, that it attacks from below, and then the double bond moves on to the oxygen.
Right, that is the right answer.
Okay.
So are you asking, now that we're sort of addressing this issue, the nucleophile can come in from above or below. So if it came in from above, I suppose that would be our product. If it came in from below, this would be our product. So I'm just trying to make sure I understand your question. You're saying you drew this one. Is that right? And the answer is yes. In fact, you get both of these. These two are actually stereoisomers of each other. We're going to call them enantiomers. You're going to get that in chapter 5, I think, so not on this test.
Okay, so we could draw either one.
Either option's okay at this point. Yep. And you'll notice that the answer I drew previously was just this, basically. When you don't use dashes or wedges, you don't mean that when you have an sp3 carbon and you don't use dashes or wedges, you indicate that both of these options are okay. Yeah.
So is that okay to write that? Like,
Yeah, it's totally okay to write it this way. For right now, it's totally okay to just write one of these. We'll deal with that later once we talk about stereoisomers. Okay, other questions? All right, so the next thing we need to do is start to figure out relative reactivity. And you've asked, how do I recognize a good nucleophile? How do I recognize a good electrophile? And being able to do that is going to rely on what right now might seem a totally unconnected concept, and that is acid-base chemistry from Gen Chem. So let me introduce this, and it's going to take us a minute to get the foundation, and then I'll show you the connection with what we've talked about before. All right. So we need to begin with a couple of definitions. When we want to evaluate how strong an acid is, we do so relative to something else, okay? So the most useful benchmark for most of the acids that matter, at least biologically, is water. So is something more or less acidic than water? And to answer this question, you basically take your acid HA and you put it in water, and then you test the equilibrium between the acid form and its conjugate base. Last week I said there's no such thing as acid dissociation. We don't go from HA to H plus and A minus. At least not in water. I guess you could do that in the gas phase. What happens here is that non-bonding electrons on the oxygen attack the Lumo, the sigma star, between hydrogen and whatever this group is, and then we break the bond between hydrogen and whatever this group is. So we have this equilibrium. There's some equilibrium constant. It can be helpful at this stage when you're dealing with an acid-base equilibrium to, sorry, I think I wanted to draw this. The other way was fine too, but this can sort of help us pay attention to what's what on either side of the equation. On the left side, HA is our acid, and water is therefore our base. On the other side, A minus is the conjugate base of the acid, and H3O plus is the conjugate acid of the base. So in acid-base chemistry, an acid always has a conjugate base. You need to get really good at drawing the conjugate base of an acid. In fact, some previous students in 351 have adopted that as a mantra that they'll say to themselves while taking the exam. I don't know how effective it is. Always draw the conjugate base. Always draw the conjugate base. It becomes very important for reasons that we'll talk about. All right. Questions so far? So, an example of this would be HCl and water going to, what should the conjugate base be? Cl minus, and then the conjugate acid of our base, H3O plus. Good. You bored yet? I'm pretty bored. Yeah. Okay. So we could, of course, measure this equilibrium constant. But in pure water, and that equilibrium constant, let's see, we could write like this. KEQ equals H3O plus concentration times the A minus concentration divided by the concentration of water times the concentration of acid. And that's our equilibrium constant. Now, at this stage, I know somebody is saying, well, hold on, it's not actually concentrations, it's activities. And the activity of a pure substance is 1, and therefore you should get rid of water. To which I'm going to say, we will not worry about activities or activity coefficients. But what I'm going to show you here actually does work out and make sense. So we're going to treat water as a participant in this equilibrium instead of ignoring it. All right, so in pure water, the concentration of pure water is about 55 molar. So what that means is that this concentration of water stays basically constant no matter what you do with some amount of uncertainty. So what we'll actually do is bring it over to the left-hand side of the equation, multiply both sides by the concentration of water, and that's going to give us this new expression. And we're going to define this equilibrium constant times the concentration of water. We're going to call this Ka, which you may have learned is the acid dissociation constant, and you may have written it like this. I'm going to put H plus in quotes because there's no such thing as H plus in water. All right. And what that does is it folds the concentration of water up into a constant so we don't have to worry about it anymore. However, these numbers vary wildly. The number can be something like 10 to the 10 or 11 all the way down to 10 to the minus 50. And that's quite a large range, and we are lazy and don't like to use scientific notation if we can avoid it. So we will do something to this Ka to make it a little bit easier for us to deal with. We're going to define the term pKa, which is the minus log of Ka. By analogy, pH is the minus log of H3O plus. That's why when we say pH 7 water, what we really mean is the concentration of hydronium is 10 to the minus 7 molar, but pH 7 is much easier to say. All right? The negative sign here is important because it switches the relationship between our value for a particular acid and then how acidic that molecule is. If we're just dealing with Ka, 10 to the 10 means there's a huge dominance of numerator over the denominator, which means that the acid is really acidic because conjugate base form dominates. And small numbers for Ka means really not acidic. It's the opposite for pKa. More negative numbers, more negative pKa values are associated with stronger acids. More positive pKa values are associated with weaker acids. Okay? So that's a trend you need to memorize and or just know intuitively. pKa's that are higher mean stronger. Dang it. pKa's that are higher mean weaker acids. pKa's that are more negative mean stronger acids. I wrote it correctly here, even though I stumbled over my words. I will say it again in an attempt to say it correctly. pKa's with higher, more positive values correspond to weaker acids. pKa's with lower, more negative values correspond to stronger acids. All right? So there's a table of pKa values in your text, and we'll just take a brief tour through them. People always ask, do I have to memorize pKa values? The answer is yes and no. There are two pKa values I want you to know. They're sort of benchmarks, and they're for water and for hydronium. So let's see. The pKa for H3O plus, and we'll what we're going to do here is generate a little bit of a table. I'm going to write HA here. I'm going to write pKa. I'm also going to write conjugate base. The pKa of hydronium is around -2. So that's a good number to memorize, -2. I think that's one of two numbers to memorize in OChem. I'm trying to think if there's more. What's the conjugate base of H3O plus? Just H2O, just water. Okay. Now, water is interesting because it is the conjugate base of an acid, but water itself is also an acid. I think in general chemistry you call these polyprotic acids. There's more than one proton to be removed or going on here. The pKa of water, going from neutral water to negatively charged hydroxide, is about 16. Okay, so this is sort of a good benchmark because we do sort of have a physical or just sort of chemical intuition about acidities. H3O plus is something you've dealt with before. OH minus is something you've dealt with before. So it's good to know those two values. Let's talk about a few things that are more acidic than, let's see if I get these wrong. More acidic than hydronium. Let's HCl. HBr and HI. HI is the most acidic. The pKa is around -11. HBr, I think, is -10. HCl is -7. If these numbers aren't exact, they're close. Go with the numbers that are in your text if push comes to shove. And I'm not going to ask you to memorize pKa values. I'll always give you a table, with the exception of I'm going to asterisk the ones that you should memorize. I will also point out at this stage that you're going to encounter alcohols that are protonated, and those also have a pKa of -2. And then you'll also encounter just a regular alcohol like water, and its pKa is also 16. Excuse me, gotta sneeze. Chew. Sorry, I don't want to spread my germs. That's people used to make fun of me and tell me my head was going to explode if I kept holding in sneezes like that. I have a brother-in-law that actually does sneeze impressions. Like, he's paid attention to how everybody in his family sneezes, and it's really kind of gross. He'll sit there and to make himself sneeze, he'll try to pull out nose hairs, and then he'll get, so it's just, yeah, sorry. It's one of those talents that you wonder if there's actually a practical use for, but anyway, sneeze impression, sorry. So let's talk about some acids that are intermediate. Oh, and I guess we should draw the conjugate bases of each of these acids. This also allows us to talk about something called the leveling effect of water. If you put HCl in water, what do you think is, which side of equilibrium do you think dominates? And we can make this decision whenever you have a question as to whether two things are acidic, which one is more acidic than the other. You can always set up the equilibrium with an acid on one side and a base here as well, and then the conjugate acid of our base and the conjugate base of our acid. You identify the acid on each side of the equation or the equilibrium, and then you find its pKa, -7 versus -2. Equilibrium goes in the direction of the highest pKa, or in other words, the strongest acid wins by losing its proton. Go ahead.
Could you define what an alcohol is again?
Oh, sorry. Yeah, an alcohol, and we'll get to this in chapter 3. An alcohol is something like methanol or ethanol or anything with just an OH group attached to carbon. Yeah. Yeah.
So to go back to your thought, the equilibrium shifts towards whatever has the highest pKa.
That's right. The equilibrium shifts to whatever has the highest pKa. The strongest acid is the one with the lowest pKa. The strongest acid wins by losing its protons. So we could tell that equilibrium would favor this side of the equation. We could conclude that HCl is a stronger acid than H3O+. So when you go to the stockroom and you buy a bottle of HCl, what are you really buying? You're actually buying H3O+ and Cl-. Okay. So what that means is that if you're in water, it may not matter what acid you use as long as it's a little bit more, as long as it's more acidic than H3O+, because at that point, that's all you can do because you got H3O+. I'll just throw this out there. If you change the solvent from water to something else, it will dramatically change pKa values. We won't worry about that at all, but that's something that's true that you might encounter at some point in the future. If not in this life, perhaps in the next. I don't even know if pKa values matter in the next life. Go ahead.
So you just said pKa will favor higher, or sorry, equilibrium should be higher.
That's right. Equilibrium, if you identify the acids on both sides of the equilibrium favors the acid with the higher pKa value or the weaker acid. Strongest acid wins in that it loses its proton. And when I say proton, I'm talking about this hydrogen. I'm not going to call it a hydrogen atom because a hydrogen atom is a hydrogen with is a proton plus an electron. So if it's H+, the H+ particle I'm going to call a proton. And therefore, when an acid loses its proton, it gets deprotonated by a base. All right, let's go ahead and take a few minutes, and we'll start up again at the hour.